Okay, one last time through the homework, through the exam. Alvarez, Lambro, Farber, Chalut, Patel. Okay, we're on the air, right? Right. Any questions? Okay, so we're now into the, I don't know if I want to say the main part of the course. Now we're into the real part of the course. Everything up to now has been, in terms of mathematics, has been very elementary because it's only been high school algebra. On the other hand, the concepts I think are difficult, so now the course kind of changes its flavor. So it becomes more algorithmic. That is, the idea now is to look at random variables in a more formal way, and to be able to handle not only discrete random variables, which is what we've been doing, but also continuous random variables, and that will mean that we're going to be making the jump from discrete math to continuous math, from addition, calculating probabilities by adding, to calculating probabilities by integrating. So to set the stage for that, let's see, I'll be on chapter 4, starting on page 129, but I'm not going to follow the book that closely. I guess it's similar to before, except that now what the author does in the book is he considers discrete random variables and continuous random variables separately. So first he does discrete random variables, goes through the whole thing, and then he repeats it somewhat for continuous random variables. So he makes a distinction because the mathematical formalities, the formalisms are different in one case than the other. But the concepts are exactly the same. So it makes more sense to me to do them in parallel rather than in series. So I'm going to talk about basic concepts and then illustrate it both through the discrete case and the continuous case. So you can see that they're both really the same thing, that the difference is only in the formalism. And in fact, in a more advanced treatment, there's a bigger formalism that handles both of them at the same time. So the separation that's in the book is really sort of artificial. But anyhow, maybe that will become clear as we go through the material. So no questions up to this point, right? Okay, so let me start off by defining a discrete random variable, which is what we've been talking about all along. So suppose x is a discrete, that's the E there, is a discrete random variable. And stuff I'm talking about here is in chapter 4 and beginning on page 129. Okay, so when I say discrete random variable, what I mean is, that is, x takes a countable number of values. In other words, we have this random variable, which is a function. And what it does is assigns to every event a numerical value. So once you do that, once you assign to events numerical values, you make the representation abstract, and it doesn't make any difference what the events represent. Then all of the rules have to do only with the numerical values the random variable takes and the probability that it takes those values. And when we say that the random variable is discrete, that means that the values it takes can be counted in the sense of there's, let's call the values T1, T2, T3, and so forth. So this is exactly what we've been doing. And in this case, we say that x is described by its probability mass function. So then, x is described, or it can be described, by its probability mass function. So now I'm making a formal definition of what we've been doing all along. Probability mass function. And that's often abbreviated PMF. And this is on page 143. Although the notation I'm using is going to be slightly different from what the author does. So first let me show you what I'm talking about. We have the probability that x takes the value t sub I is equal to p sub I for I equals 1, 2, and so forth. Okay, so what this means is that we have this random variable x, and the values that it takes we'll call T1, T2, T3, and there can be an infinite number or a finite number of them. So there's when I is equal to 1, that's T1. When I is equal to 2, that's T2, and so forth. And we call those probabilities P1, P2, and so forth. So that the once I define for you what the random variable values are and what the probability is with which you take those random variable values, then that's all there is to it. And it doesn't make any difference whether these values represent the face values of a die, or they're assigned numerical values to say heads or tails, or a particular kind of card or hand of cards. It doesn't make any difference. Once I tell you what the values are the random variable can take and the probability it takes those values, if two random variables have the same values and the same probabilities, then everything else about them is the same. And it doesn't make any difference what these things stand for. So that means that you make the subject more abstract, but at the same time that makes it more algorithmic. So now you can manipulate these things without worrying about the word meanings of things. So once you get the model set up, now you're in this place right here. Now, the author tends to call the values that the random variable takes x. So he has an uppercase x for the random variable name, and he has a lowercase x for the values it takes. That's okay if your book is printed and you can tell the difference between the fonts. But when you're writing something like this, it's much easier to give it a different letter. So I have to say uppercase and lowercase, and so they don't become confused, because if I wrote uppercase x and lowercase x, half the time you can't tell the difference. So my convention is I'm going to use t as the independent variable, and I'm going to use a lowercase, and I'm going to use uppercase x or some other uppercase letter to represent the name of the random variable. So we have these random variable values, we have these probabilities, and then the probabilities, of course, have certain properties. First of all, they must all be non-negative, and second of all, they must sum to 1. So we've already seen this, but let me give two examples, the same examples as we always have. So here's example 1. So now I'm going to say let x equal the face value of a fair die. So in this case, it turns out that the values of the random variable are directly related to the events, but they don't have to be. But in many simple cases they are, in the sense that when I roll the die, there are 6 possible face values, and they all have numbers. And a random variable always has to be represented by a number. So it makes sense to assign the values that the random variable takes to be the actual numbers on the die. And the fact that it says that it's a fair die, that tells you what the probabilities are. So that means that for this particular case, the probability mass function is this. Here's the probability mass function. So the probability that x equals, now the face values of the die are the numbers, 1 through 6. So the probability that x takes the value j is equal to 1/6 for j equals 1, 2, up to 6. So that's the probability mass function. Now, if I had some other random variable that also took the values 1 through 6 and probabilities 1 through 6, it doesn't matter whether it's a die or not. Once I write down the probability mass function, all the information at the moment is right there. Now, I can draw a picture of that. So I can draw the graph in a sense. So here is the probability that x equals t, let's say. And here's t. But in our case, the values of t are only these integers. So the values are 1, 2, 3, 4, 5, 6. And the probability that it takes those values are all 1/6. So this height here is 1/6. And of course, you can see the probabilities are all non-negative, and they add up to 1. So that's a simple example. Here's another example, example 2. So now, I should say here, let. I'm defining this. Now, I'm going to take my random variable, and I'm going to let it equal the value of a roll, which is the sum of 2 dice. So now I can write down what the probabilities are. So what can we get? Well, there's the probability that x equals 2, and that probability is, as we already know, we've done this 1,000 times, 1 over 36. And then you have the probability that x equals 3, and that probability is 2 over 36, and so on. And finally, we have the probability that, let's see, x equals 6, and that's, let's see, probably x equals 6 is 5 over 36. And then the probability x equals 7. So I'll put it in the middle. You'll see why in a moment. The probability x equals 7 is 6 over 36. But then the probability that x is equal to 8 is the same as the probability that x equals 6, and so on. So the probability x equals 3, that's the same as the probability that x equals 11. And the probability x equals 2 is the same as the probability x equals 12. So once I've told you, whether in a formula or by writing them out, the probabilities, that is the values the random variable takes, which in this case are the numbers 2 through 12, and the probability it takes those values, I've defined the probability mass function. So this is the probability mass function here. And again, as you know, obviously the probabilities are all non-negative, and if you add them up, they will all add up to 1. And now I can draw the picture of that. So let me draw that here. Because I'm running out of space, so I'll have to compress it a little bit. So the scale's going to be different. But here are the values. Here is the probability that x, which is the sum of the dice, equals t. That's t. Here are possible values are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And now the probabilities, though, are not all the same. They're different. So the probability of a 2 is 1 over 36. And the probability of a 3 is 2 over 36. And 4 is 3 over 36. And then 4 over 36. And then 5 over 36. And then 6 over 36. And then 5, 4, 3, 2, 1. And this value right here is 6 over 36 or 1/6. So the scale is different because the height of this is exactly the same as the height of that. But if I made this equal to that, then you couldn't even see those guys here. The point is that here I have 2 different discrete random variables. So I have, and I have a picture of them. Here they're all equal, and here they're unequal. So you can see these kind of characteristic patterns. So these are the 2 simple examples. And now I want to define another way that I can describe a random variable, which is not its probability mass function, but which is called its probability distribution function. So this is something that's new. This here is just repeated what you already know, so that it doesn't seem so mysterious. Okay, so I'm going to erase this. Of course, as soon as I erase it, I'm going to have to refer back to it. Maybe someday they'll have more blackboards. It's only so much you can hope for in this world. Okay, so I want to talk about what's called the cumulative distribution function. Well, first let me write the distribution function. So it's distribution function. And sometimes it's called a cumulative distribution function. Sometimes the word cumulative is left out. And this is on page 134. And this is sometimes abbreviated CDF for cumulative distribution function, or just simply DF for distribution function. And what the cumulative distribution function is it's the sum of the probabilities. In other words, the probability, now let's see, cumulative distribution function is conventionally called big F. There's a subscript X, which is the name of the random variable, and then there's a independent variable, or a dummy variable, or an argument. So this is just notation now. And what this represents, what this means is it's the probability that X is less than or equal to T. So this is a definition. So this distribution function is a function. It's a function of T, because for each T, the numerical value of big F is the probability that X is less than or equal to that T. Which means that it's the sum of the probability that X equals T sub I, summed over all I, such that T sub I is less than or equal to T. At least if the random variable is discrete, which is what we're talking about at the moment. Or in other words, equivalently, it's the sum over all I, such that T sub I is less than or equal to T of these probabilities P sub I. Or P sub J, as I could call it I, or I could call it what I call the index. Now, it's conventional to use an uppercase F, and there's also a case where you use a lowercase f. We'll get to that shortly. And one of the big things in the course, it seems to me, is that you have to be able to distinguish between uppercase and lowercase. So it's the same problem with the X's, but they mean absolutely different things. And it always seems that there are people, I don't know whether I don't know what the problem is, maybe dyslexia or something of that sort, but there are always people whose big F's and little f's look exactly the same. And they mean absolutely different things, and this is conventional notation. You have to use the notation that everybody uses. So it's always true that on the final exam, I give some random variable and I represent it by giving either its big F or its little f. And no matter which way I give it, there's always a certain fraction of the class that always misinterprets it and writes big F and little f as if they're the same thing. Of course, that's wrong. So be careful about that. We'll see that again as we go along. Okay, so this is what the definition of the distribution function is. And now, the point here, part of the point is that if I know the distribution function, maybe I should write it like this. Yeah, let me write it like this. The distribution function is equivalent to the probability mass function. In other words, if I know the cumulative distribution function, which is a sum of the probabilities, then I know the probabilities and vice versa. Now, the reason that we work with this one so far is because it's easier. It's more natural. But it'll turn out, and I'll illustrate that in a moment, that I need to work with this one because in the case of a continuous random variable, the probability mass function does not exist, but the distribution function does. So that's why we have to go, that's the essence of going from discrete math to continuous math, from sum to intervals. So again, we're going to see that in a moment. So I'm going to show that if I have the probability mass function, I can get the distribution function. And similarly, I can go backwards. So therefore, they are simply different representations of the same thing. So far, this is the only one we've needed, but later we're going to need both of these. Well, we're going to need this because this one doesn't always work. Okay, so let me find the cumulative distribution function, let's say, and I'll do it for this case and this case. Okay, so let me erase this stuff here. Okay, so I'll just draw a picture of it so you can see what's going on. So here is the distribution function of x evaluated at t, and here's t, and I'm going to use the same scale. So here's the value 1, 2, 3, 4, 5, 6. So imagine that we got these lines connected, so it's the same scale. Okay, now what I'm going to plot here is the probability that x is less than or equal to t. So if t is less than 1, then the probability is 0. But when t equals 1, the probability that x is less than or equal to t is 1/6. Okay, so this height right here is 1/6. When t is less than or equal to 2, what's the probability, or when t is equal to 2, what's the probability that x is less than or equal to 2? Well, that would be 1/6 plus 1/6, or 2/6. So at this point, it's 2/6. When x is equal to 3, or when t is equal to 3, the probability that x is less than or equal to 3 is the probability that it's either 1 or 2 or 3, which is therefore 1/6 plus 1/6 plus 1/6, or 3/6. So right up here now at 3/6. And so on. So here's 3/6, 4/6, 5/6, 6/6. So 6/6, that's the value 1. Now, these are the distribution function values when t is equal to the values that the random variable takes. But what about in between those values? Well, suppose I said, what's the probability that x is less than or equal to 1.5, for example? Well, since the random variable x only takes the values, the integer values, 1, 2, and so forth, the probability that it's less than or equal to 1.5 is the same as the probability that it's less than or equal to 1. So in other words, this graph is constant until I reach the value 2. And then there's a discontinuity, and it jumps from 1/6 to 2/6, and then it's constant, and it jumps from 2/6 to 3/6, and so forth. So you get a step function. That's what the graph would look like. So for any t, the height of the graph is the probability that x is less than or equal to t, which means it's the sum of all of the probabilities over all values of the possible values the random variable takes that are less than or equal to t. So if I give you the probability mass function, you can calculate the distribution function by simply adding up the sum of all of the probabilities less than or equal to the value t. So as I move along from t runs from minus to plus infinity here, since these probabilities are discrete, that means that only at these particular given values does the distribution function jump, and the amount of the jump is equal to the probability that takes that value. So as I move from left to right, this graph represents the cumulative sum of the probabilities for all values of t less than or equal to the value that I'm plotting. So I get a step function because as I move from left to right, the sum stays constant, then it jumps by a sixth, then it remains constant until I get to 2, jumps by a sixth, and so forth. So if I know this, then I can get this because this is simply the sum of the values in the graph above it. Now, conversely, if I knew this, I could go back to that. Because you can see immediately that if you're given this graph, whether you're given it as a picture or a formula, you can see that what this tells me is that the places where the discontinuities occur, where the jumps occur, those are the values that the random variable takes. So if I gave you this picture, you could draw this graph by saying, well, let's see. This is going to have non-zero probabilities at the values 1, 2, 3, and so forth. So where the jumps occur, that's where the random variable takes its values. And the amount of the jump, in this case each one of these is 1/6, is equal to the height of this graph. So if I know this graph, I can get this graph. If I know this graph, I can get this graph. Therefore, these two definitions, the distribution function, which is the lower graph, or the probability mass function, which is the upper graph, are equivalent. Because if I know one, I can get the other. This one is the one that's simpler, but nevertheless is still equivalent. Okay, same thing over here. Suppose I wanted to draw the distribution function right here. So here is capital F. Now, as t moves from left to right, what happens is that I'm going to have a step function, and the graph is going to jump at each one of those integer values. So I'm going to have a jump. Let's see, here's 2, 3, 4, 5, 6, and finally 12. And the first jump is going to occur at 2, and the amount of the jump is going to be 1/6, because that's the value of the height right here. And then the next jump is going to occur at 3, but now the value is not going to be 2/6, now it's going to be 1/6 plus 2/6. And then it's going to be, and then each one of these is going to add the new probability. So the graph is going to look like this. When it gets to 2, it jumps, and the amount of the jump is 1 over 36. That's the value of this probability. Then it stays constant, and when it gets here, it jumps by the amount of that, and that height, of course, was 2 over 36. So therefore, this jumps by an amount 2 over 36, which brings its height to 3 over 36. And then it stays constant until you reach 4, then it jumps, and the amount of the jump is this, which is 3 over 36, so that's going to bring the total height to 6 over 36. And so on. So it's going to keep jumping. Let's see, somehow, no, it shouldn't be 6 over 36. Let's see, 1 over 36, 2 over 36, so that would make it 3, 3 would make it 6, and so on. Okay, so we keep on jumping, and then eventually, when it added up everything, it would get to the value 1. So although it's hard to draw the scale here, I'm going to have exactly the same kind of picture, except that the amounts of the jumps are going to be different. So now the jumps are going to occur at the values 2 through 12, and the amounts of the jumps are given by the probability mass function. So this jump is a value 2 over 36, and then I add to it 1 over 36. Screw up here. Probability of a 2 is 1 over 36. So this is 1 over 36, then I add to it 2 over 36, and I add to that 3 over 36, then I add to that 4 over 36, and so forth. And when I get it all done, I've added up all the probabilities, so I must get to 1. Now, just like this, if I had this graph, I can get that graph. In fact, that's how I got it. If I have this graph, I can get this graph. Because what this graph tells me is it tells me where the jumps occur, and it tells me how big each jump is, because each jump represents the addition of a new probability. So, once again, the distribution function, which is the lower graph, and the probability mass function, which is the upper graph, are just different representations of exactly the same information. Now the question is, since this is obviously easy, and this thing seems to make things more complicated, why does anybody care about this? And so that's the point I want to make. Okay, so does this make sense at the moment? Here's a more general way of looking at it. Suppose that here is my probability mass function. So here is the probability that x equals t. And let's say that I have jumps at T1, T2, T3. Don't even have to be spaced even. So for the sake of example, there's a probability mass function. Let's call this value here P1. So that would be P1. And this value here, that would be P2. And this value here, that would be P3. So P1, P2, P3. Those are the heights. Now, the distribution function for that, in this case where we have 3 possible values, we would have jumps at T1 and T2 and T3. The height of the jump right here would be P1, so this height would be P1, and the height here would be P1 plus P2 because I would add to it that value. So this height now is P1 plus P2, and the height at this point would be P1 plus P2 plus P3. And if there are only 3 of them, that must add up to 1, so the graph would look like this. 0, and a discontinuity, then a constant step, and a discontinuity, and a constant step, and a discontinuity there. And the final value is necessarily 1 because it's the sum of all the probabilities. So in other words, I start at 0, and then I have a step function, which as I move from left to right, jumps by the values equal to the probability. So it accumulates or sums the probabilities, and when it finally ends, it has to be up to the value 1. Okay, so this seems simpler than this. So let me ask this question. Suppose that my random variable is supposed to represent this. So x means choose a number in the interval 0, 1 and choose at random. So that means that all numbers are equally likely to be chosen. So that makes sense. I mean, this is, if you can't answer this kind of question, then forget it. This whole subject is useless. So here's the interval 0, 1, and I'm going to pick out a number at random. This is what the random number generator, in principle, in the computer does, and we're going to study this in great detail, because we're going to have to understand how you can use a computer to simulate any probability distribution, whatever. So this is equivalent to, say, spinning this dial. I take this dial, I flick it, it goes around the circle, it picks out some number. And when I say that all numbers are equally likely to be chosen, that means that it's no more likely to point here, or here, or here, or here, or any place. So it's sort of like going up to the board here, closing your eyes, and then drawing a line, or drawing another line, and so forth. So these are the values that I'm going to pick out. And I want to ask, what's the probability that when I conduct this experiment, when I spin this dial, when I generate a random number, that the value that I get is some specific value, like t. So how am I going to do that? Well, the problem is that I have an infinite number of points in my sample space. In fact, it's uncountably infinite. So one way to do it might be this. Here's my interval from 0 to 1. So what I'll do is I'll divide it up into little subintervals. And each interval has length 1 over n. So I'm dividing it up into n intervals. And then I'll say that a number corresponds to falling in a particular interval. And then the probability that I pick any particular number is the probability that I fall in that interval, where that contains that interval, which would be equal to 1 over n. But of course, that's only an approximation because I've just divided this up into intervals. I've said the intervals are all equally likely, but the interval contains lots of points. And so this is only going to be accurate in the limit as n goes to infinity. So of course, if I take the limit as n goes to infinity, the result is 0. And that sort of makes sense because what you're saying is each number is equally likely, but I have an infinite number of equally likely numbers. Well, if the probability associated with each number is the same, and if I add them all up, I have to add up to 1, how can I add up an infinite number of non-zero equal values and have it add up to 1? Well, it's impossible, because that means either the probabilities all have to be 0 or the sum will be infinite. So the answer is that the probability that x takes any specific value is in fact 0. So that's the true answer. If I say pick a number at random in an interval from 0 to 1, and all the real numbers between 0 and 1 are eligible to be picked, and they're all equally likely to be picked, then the probability that any particular number is picked is 0. So that may be the correct answer, but it's not very helpful, because you can't calculate much. In fact, you don't even have a probability mass function for it. It doesn't exist, because these probabilities do not sum to 1. But there's no way to make them sum to 1 and still have a positive equal probability for every point in this region. And in fact, this is true in general of any continuous random variable. If I have a random variable that takes an uncountably infinite number of points, then there is no way to calculate the probability that it equals any specific point other than to say the probability is 0. Now, people have a lot of trouble with this, and in fact, on the final exam, I usually ask a question in which I have some random variable, and I give either its, I describe it somehow, and then I ask for various probabilities. And one of the probabilities I ask for is just say what the probability of a certain number. And half the people in the class calculate that by plugging the number into the distribution function, and of course, they get it wrong. The answer is 0. So you have to think about that a while, convince yourself. But the only thing that makes sense here is to say that the probability that any particular value occurs in advance, if I tell you in advance and ask you the probability for any particular value, its probability is 0 if the random variable takes its values in a continuum. Now, that doesn't mean that it's impossible. After the fact, when I spin this dial, I've gotten some number. So in a discrete case, the intuition is that if an event cannot occur, its probability is 0, and if its probability is 0, it can't occur. But in general, that's not true. If the event can't occur, its probability is 0, but if its probability is 0, that does not mean that it can't occur. It just means that it's one value out of an uncountably infinite number of possible values. So we want to be able to talk about random variables that describe things other than cards and dice and points. You want to be able to talk about time and distance and things like that. So just as in order for mathematics to be useful in engineering, you have to go from discrete mathematics to continuous mathematics, which means to calculus. It's exactly the same thing here. So we're making exactly the same step up. We want to be able to talk about random variable values that are not required to be discrete, but they can take any values at all. So we have to be able to describe them, and we can't describe them with the probability mass function because the probability mass function does not exist. So if x is a continuous random variable, then its probability mass function does not exist. But that doesn't mean we just throw up our hands and quit. That means that we have to do something else. And something else is we have to look at the probability distribution function. Because it will turn out that the probability distribution function does exist, even though the probability mass function does not exist. Okay, so let me convince you of that by looking at a particular example. This example. Okay, so for this example, continuing on here, the probability that x equals t is equal to 0 for every t. Everybody agree with that? I mean, if you don't agree, it just doesn't make any sense, then of course nothing in the future makes any sense. Okay, so we have a sample space with an infinite number of points in it. It's actually an uncountably infinite number of points, which is what you have in in at least the idealization of all measurements of things like time and distance, for example, uncountably infinite number of points. And your random variable value is going to be one of those points. And so the probability that any particular point, because there's an uncountably infinite, gigantic number of them, the probability that any particular one is picked out is 0. But nevertheless, the sum of all possible values, if I add them up, must be 1. And how can that be? Well, what I'm going to be adding up is an infinite number of infinitesimal values, which is what calculus does. When you calculate an area in calculus, what you're doing is you're adding up an infinite number of infinitesimally width, of strips of infinitesimal width. And the idea is that when you add those things up, you get an area which is not 0. Even though you're adding up each individual strip as with 0, there's so many of them that in some sense the infinite number compensates for the fact that each one of them has 0 value. And you get that by taking limits. Okay, so we're going to be doing the same thing here. So what I want to ask is, let's look at this particular problem and see if we can calculate the distribution function, which, remember, is the probability that x is less than or equal to t. Okay, so let me draw the graph of this distribution function. So here is capital F. And often, by the way, you don't have to put this subscript in here, because the subscript tells you which random variable the big F refers to. If there's only one random variable, then you don't need to write the subscript all the time. So then you can just write capital F. This is usually written if you want to indicate what this means. If I didn't put the X here, then you wouldn't know what this statement means right here. But otherwise, once I get beyond having to write what the statement means in this sense, then I can simply write capital F unless I have more than one random variable. And then I would have, say, f sub x, f sub y, f sub z. I always want to use f for the distribution function, and the subscript tells me which random variable that's the distribution function of. Okay, so I'm going to draw the graph of the distribution function of x, where x represents this experiment of spinning this dial and picking out a point at random. That's what that picture's supposed to do. Okay, so we know that the answer is going to lie between 0 and 1. That is, whenever we spin the dial, we're going to get a number between 0 and 1. Now, this represents the probability that x is less than or equal to t. So let's look at numbers that are negative. What's the probability that if I spin that dial, or equivalently, I pick out a number at random in this interval, that the value that I get will be negative, will be less than or equal to a negative number? 0. That never happens. So for every t that's negative, this distribution function has value 0. Okay, how about t greater than 1? For example, what's the distribution function of x evaluated at 3.7?
0.
1. Because remember, this represents the probability that x is less than or equal to that. So since the numbers all lie between 0 and 1, for any t that's greater than 1, I will always be less than that. So therefore, the distribution function is going to have the value 1 for every value t that's greater than or equal to 1. All right? You have to remember, distribution function represents the probability that x is less than or equal to t. The probability that x is less than or equal to 1 is 100% because all the numbers lie between 0 and 1.
But you just said the probability that x takes any specific value is 0.
That's right.
Then you say, well, what if it's 0.37? That's 0.
No, remember what I said. I said that the fact that the probability is 0 does not mean that it cannot occur. So when I have a continuous random variable like this, every time I conduct the experiment, I'm going to get some number between 0 and 1. But the probability that I would get any specific number, if I said, what's the probability I get 0.7, the answer is 0. That's why we're doing this, because the probability of getting any particular value is 0, but when the experiment is conducted, we get some value. So it makes, you have to come up with a different way of handling it than simply say that the probability that x equals something is 0, because it doesn't tell you anything. Okay, so the question then is not what's the probability that x is equal to t, what's the probability that x is less than or equal to t. Now, if I take a t that's greater than 1, since all the values lie between 0 and 1, the probability that when I conduct this experiment, I'll get a value that's less than or equal to some number that's larger than 1 is 100%. So for any t that's negative, the distribution function has value 0, because I am never less than or equal to a negative number. And for any number that's greater than 1, the distribution function has the value 1, because I always get a number that's less than or equal to a value that's greater than 1. All right, now what about the stuff in the middle? Suppose I said, what's the probability that x is less than or equal to 1/2? So here's 0.5. Yeah, it's 0.5 because in our model, what we're assuming is this. We're saying, well, what I'm going to do is I'm going to imagine, this is the model, that even though there's an infinite number of numbers and they're all, and each of them has probability 0, nevertheless, they're all equally likely. So that means that if they're all equally likely, then half the time I should fall in this interval, and half the time I should fall in this interval. So the probability that I am less than or equal to 1/2 is the probability that I fall in this interval right here, and that should be 1/2 by our model. Okay, how about 0.75? What's the probability that if I spin this dial, the value that I get will be less than or equal to 0.75? Well, if all numbers are equally likely, and equally likely means this, here's another way to think of it. Here's 0, here's 1. I spin the dial, I get some value. I can't predict it. All I know is it's going to lie between 0 and 1. I do it again, I get some value. I do it again, I get a value. Well, if I do it a zillion times, even though the outcome of each particular time is unpredictable, you could see that if what I mean by this is all numbers are equally likely, then I should get a pattern that in the end would be a uniform shade of gray, like that. Because if it weren't, if it tended to give you patches that were dark and light, that would mean that it would have a greater tendency to land where the dark patches are, which means that those numbers would be more likely than the other numbers. So if I assume that all numbers are equally likely, what that means is that the values are going to spread out in a uniform shade of gray if I made a zillion of them, even though each individual one is unpredictable and the probability of any particular one is 0. So if they're going to spread out evenly in the long run over that interval, then if I looked at 0.75, that means that 75% of the time I should fall here, and 25% of the time I should fall here. So f of 0.75, which is the probability of being less than or equal to 0.75, that should be 0.75. So here's 0.5, here's 0.75.
So you get a diagonal line going from 0 to 1.
Exactly. Okay, so here's 0.5, here's 0.75. So you can see now that if instead of giving you a specific number, I said, what's the probability that x is less than or equal to t, where t is simply some number that lies between 0 and 1, the answer is, well, it's the ratio of the length of that interval, which is t, to the length of the total interval, which is 1, or in other words, t. So the graph, if I were to draw it, should look like this. In other words, here is my distribution function. The distribution function of x evaluated at t is equal to, it's 0 if t is negative. It's t if t lies between 0 and 1. And it's 1 if t is greater than 1. So I have a distribution function, but the probability mass function doesn't exist, because the probability of every point is 0. Now, you probably recognize this. This is a distribution function for what's called the uniform distribution, which is one of the examples I used in homework 0. And so, in this case, that is, if that's a distribution function, x is said to be uniform in the interval 0 to 1. So, in fact, in general, you can have a random variable that's uniform between a and b. That is, I'm going to pick out numbers at random in this interval, and I can never pick out a number outside the interval. So instead of 0, 1, it's a to b, and the uniform is the idea that you have a straight line. Or in other words, that the pattern gives a uniform shade of gray rather than tending to concentrate in one place as opposed to another. So there are all kinds of random variables with different distribution functions, just like we have all kinds of discrete random variables with different probability density functions, probability mass functions with different PDFs. This is just one of them, and it turned out to be one of the most important ones, and it's the one called uniform. So this is it. This is homework 0, and we'll get back to this in detail later. What I'm getting at now is this is an example, first example, maybe the most important example, of a random variable for which there is no probability mass function, but which there is a distribution function. And obviously, if probability can't handle the question of simply picking out a number in an interval, then it can't do anything. So you must have this. So what we see is that if a random variable is discrete, it has a probability mass function and a probability distribution function. If the random variable is continuous, it does not have a probability mass function, but still has a probability distribution function. So therefore, the distribution function is more fundamental than the probability, that is the, let me say that again. The probability distribution function is more fundamental than the probability mass function, even though the probability mass function is simpler in the discrete case. So now we got to go back, and what we have to do is we have to look at in more detail at how probability distribution functions work, how they provide the same information that we already knew how to get, except that instead of calculating probabilities by adding things up. Remember that if we had a particular case here and we had discrete probabilities like this, if we wanted to find the probability that a random variable lay in a certain set, what you did is you added the probabilities for all of those numbers in the set. Now, if you want to find the probability that a random variable lies in a certain set, you have to add the probabilities again, but each of them has probability 0. So when you add them up, in effect, what you're doing is you're integrating. And so we're going to connect the distribution function to something called the density function, which is the derivative of the distribution function, whose integral then gives you probabilities. So what we're doing is we're just upgrading the level of random variables that our theory can handle. But all the questions we had before, like what's independent and what Bayes rule and probability of unions and intersections and all that, everything is the same. The only difference is that the calculations are made in a different way. So the concepts are the same, but now instead of adding probabilities, we integrate what's called the density function. Okay, so let's look then at properties of distribution functions. So, can I erase this stuff? Is there any question here? Okay, so the question I want to ask is, look at this. Here we have this random variable, and here's a value A, and here's a value B. And the question I want to ask is, well, first of all, let me say that the probability that X is less than or equal to B. What's that probability? Well, we can see that that's the probability of the union of two events. It's the probability that X is less than or equal to A, plus the probability that X lies between A and B, excluding the A, including the B. So this is obviously a true statement, whether the random variable is discrete or continuous. So now, we know that the probability, if the random variable is continuous, the probability that it equals any specific value is 0, but I can still calculate the probability that it lies in a specific interval. So the question is, what's the probability that x lies between a and b? Now, at the moment, there's a little unsymmetry here because I have a less than sign here and a less than or equal to sign here, but it'll turn out that that's not important, and that when we worry about continuous random variables, in effect, it doesn't make any difference whether I write less than or equal to. The reason being that the probability that it's exactly equal to is 0. So in the continuous case, it doesn't make any difference whether I'm careless or not with these signs, because adding or subtracting a single point has no effect, because the probability of being at any specific point is 0. Anyhow, what we want to do is we want to calculate this probability here. So you can see I can get that by simply putting that, by just putting this on this side of the equation and then reversing. So this thing is the same as the probability that x is less than or equal to b minus the probability that x is less than or equal to a. But by the definition of distribution function, this is the distribution function of x evaluated at b minus the distribution function of x evaluated at a. So if I know a random variable's distribution function, whether it's discrete or continuous, I can always calculate the probability that it lies in any particular region, because I just have to use a distribution function. So every question that can be answered about a continuous random variable can be answered using its distribution function. Just like, same is true for the discrete case. Except in the discrete case, I could also answer it by using the probability mass function. In the continuous case, there is no probability mass function. Okay, so let's see. This is in the book. This stuff here is on the bottom of page 135. Of course, there it's for the discrete case. And in the discrete case, you really don't care about this, because you don't need it. In the continuous case, you absolutely need it. So that's why I'm doing it differently from what the author does, because talking about this for the discrete case, unless you understand the continuous case, all you're doing is taking easy problems and making them harder. So I'm going to do continuous and discrete together, but that means that when I write down results, some of them are going to be on page 135 and some of them are going to be on page 235. Because the author doesn't get to the continuous case until after he finishes the discrete case, and so it takes 100 or so pages to do that. All right, so let me write down, let's see. Let me write down what the properties are. I think I'll do it here. Because I want to refer to this diagram over here as an example. So I want to write down the properties of distribution function. Properties of capital F. So first of all, what must we have? The distribution function, I'll put the subscript there, at minus infinity must be what? Let's see, before I do that, remember that we had the properties of the probability mass function. What were the properties? The probabilities had to be non-negative, that had to add up to 1. Any set of numbers I give you that are non-negative and whose sum is 1 could be a probability distribution. That is, they could describe a random variable. So whether they do or not, that depends on what particular model you're using. But if you want to be mathematical about it, you're talking about probability mass functions, what you're talking about is sets of non-negative numbers whose sum is 1. Okay. So what are the properties that the distribution function must have? So I have to tell you this is a function. I have to tell you what it is in such a way that you can identify any particular function and say, yeah, that could describe a random variable, or no, it can't. So what is the value of capital F at minus infinity? 0. It's 0. Because what it means, it's the probability that the random variable is less than or equal to minus infinity. So we simply say when we define random variables, that random variable values are numbers between minus and plus infinity. Because minus and plus infinity are not themselves numbers. Okay, in the diagram here, f of minus infinity is 0. And the same thing where we had the distribution function of a sum. So let me go back over here and draw the particular cases. Discrete looked like this. So every discrete always had the property that it has a step function and it goes between 0 and 1. And continuous, at least the one we looked at, looks like this. So here was our example. Discrete is always a step function, and continuous is not a step function. Okay, so in either case, f of minus infinity must be 0. Okay, so what about f of plus infinity? It's 1. So the function always starts at 0, ends at 1. Okay, now comes the key statement, which is that if A is less than B, then the distribution function of x evaluated at A must be less than or equal to the distribution function of x evaluated at B. Okay, let me erase this here. So what this says is that, in other words, f is non-decreasing. In other words, as I move from left to right, the function either stays the same or gets bigger, but it can never get smaller. So you can see that here. As I move from left to right, between jumps, the function stays the same, and at jumps, it gets bigger. So it never decreases. It either increases or stays the same. Likewise over here. As I move from left to right, the function either stays the same or increases, but it never decreases. So a distribution function cannot oscillate. So it's a simple function. And in fact, physically you can see why this is, because remember that the distribution function represents a cumulative probability. It's the sum of all the probabilities for all of the events up to that particular numerical value. So what that means is that as the argument gets bigger, the probability that x is less than or equal to that value cannot get smaller. It can stay the same, it can increase, but it can't decrease. As I take a bigger and bigger set, the probability of being in that set can't get smaller. Okay, so those are the main things, and now there's one other one which I'll write down for mathematical completeness. 4. Distribution function is what's called right continuous. Now that's just a mathematical statement which you can ignore, but which I'm psychologically incapable of leaving out because it should be there. Okay. What it says is that the random variable is continuous, right there. Any random variable that's continuous is also right continuous. Right continuous means that if there are discontinuities, then the function is defined by the jump on the upper part. So to say that the function is right continuous means that whenever there's a discontinuity, the function is defined there. So it's continuous on the right-hand side, and the discontinuity is on the left. Now remember that in the discrete case, you rarely use this anyhow. You don't care about this. In the continuous case, continuous by definition means continuous. So in fact, this really has no effect. But if you're trying to be precise about it, what you say is, what's a distribution function? Any function that has the property that it starts at 0, it ends at 1, it's non-decreasing, and if it's discontinuous, it's right continuous. Any such function could be, or is, a distribution function, and could be a description of a random variable. And if we know this function, then we can calculate the probability of lying in any interval, because we know that the probability that x lies between A and B is equal to the distribution function of x evaluated at b minus the distribution function of x evaluated at a, and we know that the probability that x equals any specific value is equal to 0. So, in other words, this is always true, and this is if x is continuous. Okay? Okay, so now, what do we do with all this stuff? Okay, suppose I wanted to calculate the probability that x lies between a and b. So suppose x is discrete. So what do? What you do is you would say, I'm going to calculate the sum of the probability that x equals a particular value t sub I, and I would add it up over all values of I such that t sub I lies between a and b. I mean, that's what you've been doing all along. When I say what's the probability that if I roll 2 dice, the value turns out to be between 7 and 9.5, what you would do is you would add up the probabilities for all the values that the random variable can take that lie between, what were the 2 numbers I said? Well, I want to find the probability that if I roll 2 dice, that the sum lies between 7 and 9.5. So then I would add up the probability for all the values between 7 and 9.5, whatever they are, however many there are. In other words, I would add these up for all values of the t sub i's that lie between the 2 values I asked for, 7 and 9.5, and whatever that sum is, that would be the answer. And in fact, we already know that that's equal to the distribution function of x evaluated at b minus the distribution function of x evaluated at a. Whether it's discrete or continuous, we know that this is true. Okay, so now suppose that the random variable is continuous. Okay, now what's this probability? Well, you can't get that by adding up the probabilities because they're all 0. But there's an infinite number of them. And we know that when we get done adding them up, whatever that means, the answer is going to have to be given by this. So let me tentatively write the answer this way. Instead of a sum, I'm going to write integral. And instead of the probability, I'm going to write something else, which is a lowercase f. This is an important point now. This is a lowercase f, not an uppercase f. And then I'm going to take this so-called density function, which is analogous to the probability mass function. But instead of adding, I'm going to integrate between a and b. And in either case, I'm going to get the same answer, because we know what the answer is. So now the question is, okay, what I have to do is I have to come up with the so-called density function. That's the density function. And the density function is a function that's analogous to the probability mass function. But it's not a probability, because the probabilities are 0. But it's a function such that if instead of adding them, I integrate over the same range, I get the same answer. So then I have a sort of a symmetry here. Because if the random variable is discrete, if I tell you this, you can get that. If I tell you that, you can get that. I already illustrated that. If the random variable is continuous, then this probability is given by that. So what I want to do is I want to come up with another function such that if I integrate it, instead of summing it, the result will be the same. Which means that if you tell me this, I can get that. And it'll also mean that if you tell me that, I can get that. So in other words, there'll be a direct correspondence between discrete and continuous. The difference is that the formalism is sums here and integrals here. But that's the difference between discrete mathematics and continuous mathematics. But nevertheless, it represents the same thing because this integral represents adding up strips that correspond to the area under this curve. So we need two things. Let me draw a picture first. Well, no, first let me state, I got 3 minutes. I'm going to state the fundamental theorem in calculus again. You'll see the analogy, and then we'll discuss this in more detail next time. Okay, so here is the fundamental theorem in calculus. Suppose I have some function, I'll call it g of x. I want to call it f because I'm using f for something else. So here's my g of x, and here's some a, and here's some b, and I want to find the area. So the area between a and b. I'm going to call that, so I'm going to define that as this symbol. So I say to you, okay, what I want to do is I want to find the area under this function, g, between a and b, and I'm going to tell you that I'm going to denote that by this symbol. You don't know what it means. All it says is I see this, I say, okay, take the thing that's between those two symbols and find the area of that as, or x lying between that value and that value. Okay, now, how do I find that area? Well, this is what the fundamental theorem of calculus says. It says, let capital G of x be such that the derivative of big G is little g. If I have another function whose derivative happens to be the function whose area I'm trying to evaluate, then this area is given by this new function evaluated at the upper limit minus the new function evaluated at the lower limit. So the fundamental theorem of calculus comes right in here. Fundamental theorem of calculus. It says, I want to find an area. I call area by this name. Then I say, how can I figure out what that is? And the fundamental theorem says, well, what I need to do is I need to find some function whose derivative is that, and then plug in to that new function the upper limit, the lower limit, and subtract it. And if I do that, I'm home free. Why does that work? Well, you've got to ask Newton and Leibniz. Okay, we'll go over that. But let's say it does work. What does this mean? Go over here and look at this by analogy. What this thing says is that I want to find a function, capital F, which I evaluate here, and I evaluate here, and I subtract them. And I want to find something that's analogous to adding probabilities, but the probabilities are all zero. So what I will do is I will come up with another function, and I will find the area under that function between those two limits, and it'll give me the same answer. And this function, which is the so-called density function, is the derivative of this function right here. So that means that if I can find a function which is a derivative of the distribution function, the probabilities then are the areas or the integrals under that density function. So once I understand density function is analogous to probability mass function, even though the density function values are not probabilities. Okay, so this is a big calculus lesson, and we're going to do this so many times that it'll get boring in a short time, and it won't be so mysterious. I'll go through lots of examples, then you'll get it simulated. Everything will hang together, I promise.